So let's have the analysis of two-dimensional frames. The stiffness matrix is 6 by 6 and it's also very difficult to memorize. So during the regular classes, I usually allow my students to have the index card to write the member stiffness. And it's the development of the stiffness should be, since it's very difficult and it's boring to use the matrix approach to frames, you can only appreciate this if you have a matrix calculator. So I will share with you my matrix calculator, but not the ready-made one, just to give you the idea. So for problems, I make sure that there will only be 3 degrees of freedom. So a 2D frame element has 3 degrees of freedom per node, the axial, the horizontal translation, the vertical translation, and the rotation. So that's why 3 at each end. There are 2 ends of a frame element, so that makes it 6 by 6. And with rotation. So in beams, there were only 2 degrees of freedom per node, but this time we incorporate the effect of axial effect to frames. So let's consider this frame element. So these are the forces at each node that will contribute to displacements. The shear, the axial displacement, which is independent of the shear and moment effects. So in other words, the axial effect is purely axial. It has no contribution to shear and bending. So that's the axial effect. Then we have the shear effect, delta 2. These are the positive displacement directions. Then the rotation, call that delta 3. So the marking, remember, horizontal movement is 1 or K11. Then the vertical movement is K12. And the rotation is delta 3. It may be represented by K13. Then we have delta 4, horizontal movement, delta 5, vertical movement, positive displacement, and positive rotation counterclockwise, delta 6. So these are the properties of the frame element. We have length, area, and modulus of elasticity. So we note that axial forces are independent of shear and moment forces and vice versa. So the displacement due to axial effect cannot contribute to displacement due to shear and rotation. So in each row, it's only due to axial effect. So here we note that rows and columns associated with numbers 1 and 4 are the only non-zero elements. So row 1, row 4, or column 1, column 4 will have force coefficients, and for the rest, it will be 0 for these particular numbers. So the elemental stiffness matrix for a frame member is, in terms of the local coordinates, will be as follows. So K of the element is, you just look at rows 1 and column 4. It is where the axial effect is present. So for the rest, it will be 0. Then we have AE over L. Remember for bars, we have AE over L. Then 0 for the rest. Then negative AE over L for column 4 or row 4. And between and for the other numbers 2, 3, 5, 6, it will be the same as that of the beam element. Can you see it? So remember, this is the stiffness of a beam element. These are the force coefficients of a beam element. We just include the effect of axial, which is at row 1 and row 4, or column 1 and row 4. This is the stiffness for bars. You can remember. Then 2, 3, 5, 6 would be the force coefficients for beams. So this is the local uh, stiffness of a frame element. Now we incorporate the rotation as in truss elements because some frames are inclined, not always horizontal or vertical. There are also inclined frames. So there's a need to have this beta transformation matrix. So the transformation matrix for the frame element is, let's consider the frame element shown and the local displacements so that we can relate them to the global displacements. Local displacements are the deltas and the global displacements are the u's. So that's it. So we have u1, u2, delta 4, u4, delta 5, and u5, and rotation delta 6, u6. We take note that the local rotation and the global rotation are the same. Again, the local displacement for rotation, because it is rotation about an axis perpendicular to the plane, so it is the same because it is rotation counterclockwise, counterclockwise. So that's why delta 3, delta 6 are respectively equal to u3 and u6. So just as truss element, we can write the following equations. So the displacement 1 local is u1 cosine theta plus u2 sine theta, if you can remember. Delta 2 is negative u1 sine theta plus u2 cosine theta. Then delta 3 would be due to axial only. Delta 3 and u3 are the same. So delta 3 equals u3. Delta 4 would be u4 cosine theta. U3 cosine theta. U4 cosine theta plus u5 sine theta. That's delta 4. Delta 5 is negative u4 sine theta plus u5 cosine theta. And delta 6 is also u sub 6. So writing this in matrix form, and remember that delta is equal to beta times u. So beta is equal to, we have for 1c, column 2s, then 0, 0, 0, 0. Because there is no u3 here, u4, u5, u6, everything is 0. Then for delta 2, we have negative s, u1 sine theta, so negative s, cosine, then 0, everything is 0. For this third equation, it's only 1 at row 3, column 3. The rest is 0. Then 4, fourth, cosine, fifth, sine, the rest 0. For fifth, it's fourth, everything is 0 except for fourth, which is negative S, fifth, positive C. Then delta 6 is U6, so meaning to say 0 up to 5, then 1 at the 6th cell. So this is the value of beta, just like for truss elements. So Ke global is equal to beta transpose times Ke stiffness of individual element times the beta matrix. Remember that inverse of beta is equal to the beta transpose because of orthogonality. So Ke global therefore is equal to this beta transpose, the transpose of this matrix here, times the K sub E, which is at 1 at 4 AE over L, negative AE over L, positive AE over L. Then the rest is the same as that of the beam element stiffness, same as that of beam element stiffness, multiplied by beta, which is this. So if we perform the multiplication, including this beta here, so the result would look like this, and it is a symmetrical matrix. So this is therefore the global stiffness matrix of a frame element. Since it is 6 by 6, although we only have to fill up the upper right triangular matrix because it is symmetric, but still it's difficult to memorize the force coefficients of elements. So this is the result. I always allow my students to have this in their index card for frames, but I usually not give problems on frames and solve it by matrix approach. You have to make a matrix calculator so that you can appreciate analyzing frame elements, because the solution is very lengthy. The fact that the global stiffness matrix of a frame element is 6 by 6. So that's it. So problems that I prepared are those with only 3 degrees of freedom, and there are a lot of problems on frames that is at least 6 by 6. So that's why um, if you have time, I want you to make your own matrix calculator for frames so that you can easily input the characteristics of the frame element or properties of frame element. Then when you set up this in Excel, you just after you input the properties of the frame element, then with little analysis on the nodal loads, then you finally wait for the answer. You can determine that. You can find the answer immediately. So that's it. I will not require you to memorize this because you're allowed to have this in your index card. So for the member forces, remember that it is the K of an element. So remember this is the K sub E, then the beta, then the global displacements, which are solved after we assemble the global stiffness matrix for each element and solve only those uh, displacements, required displacements after we eliminate rows and columns associated with zero displacements. So if we expand this, the result would look like this. But in my matrix calculator, the member forces, which is represented by this matrix, I did not uh, prepare my matrix calculator in this manner. Instead, I use this Ke, then beta, then the U, because after we solve for U, we can easily operate matrix multiplication, even if it is more than 6 by 6, or even if it is 10 by 10 or 12 by 12 matrix. So just remember the stiffness, local stiffness matrix of the individual element and the data matrix. Then you can compute the force matrix or the member forces matrix. So I'll stop here para di masayang ang record. In this problem, there are 3 degrees of freedom, so you can use your calculator here. So determine the nodal displacements and member forces of the frame shown. E is 200 gigapascals and moment of inertia 500 times 10 to the 6 mm to the 4th. The cross-sectional area of each member is 30,000 mm square. This 30,000 mm square, when converted to meter square divided by 1,000 square, is 0.03. 0.03. So this is the frame. This is very easy if you solve using slope deflection equation. You can also use free moment equation here from theory 2 because there is no side sway. So I mark the joints as B1, A is 2, then 3. So we have member 1, 1 to 2, BA, and member 2, 1 to 3. So the stiffness of member 1, 1 to 2, or AB, or BA, the cosine is 1. This is BA, supposedly B to A. The cosine value is 0 because it is vertical going down. The sine is -1 because it is going down. So remember BC, the cosine is 1 to 3, so it's horizontal. So cosine is 1 and the sine is 0. So there are only 2 members. Then let's have the stiffness of each element. This is the guide. This is the guide. Then you evaluate AE over L plus AE over L times cosine square, then plus 12 over EI L cube times quantity sine square. So for member AB, for example, the cosine is 0, so this part is 0. Then we only have 12 EI. We may assume EI is 1 because it is constant, divided by L cube, so divide by 6 cube, then times sine square, which is equal to 1 because sine is -1, so 1 square. So let's check. KAB global is equal to, so it is numbered 1 to 6, so U1 up to 6 also. So for member BA, you evaluate 12 times EI, by the way, is, I incorporated EI here. So EI is 200 times 200,000 times 500 times 10 to the 6 divided by 1,000 cubed. So it is 100,000. So 12 times 100,000 divided by 6 cubed. Try to calculate it. It is 50,000 over 9. Then because cosine is 0, this is SC, this is SC. So the product would be 0. So that's why it's 0 here. So sine is 1. So there is value -6 times 100,000 divided by 6 square times sine, which is -1. So this value is positive, 50,000 over 3. Then, and so on and so forth. You just evaluate these items in each cell here, the upper triangular matrix. Then after that, you copy because it is symmetric. So 500 over 3, -50,000 over 9, 0, 50,000 over 3. And that's why we have 0 here, 50,000 over 3. -50,000 over 9. This is only 5,000 over 3. Let's compute row 1, column 4 again. Row 1, column 4. So this value here. So it is the negative of the first entry. So it should be 50,000 over 9. I'll just correct this later. Then for member BC, KBC Global, so it is the cosine that is 1, the sine is 0. So that's why we have here A 0.03 times 200. This 200 here is 200 times 10 to the 6 kilonewton per 200,000, 200 times 10 to the 6 kilopascals. So area is 0.03, E is 200 to the 6, then divided by L. So divided by L, which is 8. So we have 750,000 times cosine square. So cosine is 1, so it is 750,000. So here we have S and C's. One of them is 0, so the whole value here is 0. Next, negative 6EI, so sine is 0, so that's why it's 0. Then this is the negative of the first row because the second term is 0. So negative 750,000. Still we have SC, so 0. The product SC is 0. S is 0, so everything is 0. You copy it here. This one is 12 EI over L cubed. So 12 times 100,000 divided by 8 cubed. 8 cubed. So the result is 9375 over 4 or 2343.75. So I think there's no need to explain this. You just evaluate the entries here. Upper right triangular matrix, then copy in the lower right in the lower triangular matrix. So these are the stiffnesses for member global stiffness matrix for each member DA and BC. So we only want the nodal forces at node 1 represented by U1, U2, U3. These are the unknowns. And at 2, everything is 0. 0 horizontal, vertical, and rotation because these are fixed, as well as at 3. So we can reduce the global matrix into 3 by 3. We are only interested of 1, 2, 3. So 1, 1 is 50,000. 50,000 over 9 plus 75,000. That's it. So fixed moment BC is WL square over 12. That's the formula. So 320 over 3. It is counterclockwise at B fixed forces, but the nodal forces would be clockwise. So clockwise is, remember, negative. So 320 over 3. We also have fixed end force, which is the reaction, equal to 20 times 8 over 2. So FBR equals FCL equals 20 times 8 over 2, so 80. So there's no axial force, so the forces are only vertical, and that is delta, that is F2, and rotational F3, so 320 over 3. This is negative. This is also, this is the fixed force, which is upward, so the nodal force is downward, so that's why it's negative 80. So if this is node 1, the nodal forces would be opposite to these values here. So because 80 is upward, that's a reaction, so the nodal force should be downward or negative 80. This 320 here, remember, is counterclockwise because at the right it's clockwise. So that's the fixed force. Therefore, the nodal force is 320 over 3 clockwise or negative. Then let's assemble the 3 by 3 matrix, global forces. So along X or axial 0 at node 1. And we have the vertical load negative 80 and moment negative 320 over 3 because that's clockwise. Then 1 is the sum of 750,000 and 50,000 over 9. We also fill up the supposedly 6 by 6 matrix 1, 2, 3, 7, 8, 9. But this is the global stiffness matrix of BC. We only fill up 1, 2, 3 because those nodes are associated with unknown displacements. The rest zero displacement. So 1 is 6,800,000 over 9. 1, 2, we have 1, 2 here, 0, plus 0 here, so it's 0. So this is also 0. Then this is 1, 3. 1, 3, we have 50,000 over 3, plus 0 is 50,000 over 3. That's why this is also 50,000 over 3. 2, 2 is 2,343.75 plus 1 million. So it is 1,2,343.75. Then this is 2 row 2 column 3. Row 2 column 3 is 0 here. But here row 2 column 3 is 9,375. So row 3 column 2 is also 9,375. It is symmetric. And finally 3, 3, we have 200,000 over 3 here. Then on the other matrix, we have 50,000. So 200,000 divided by 3 plus 50,000 is 350,000 over 3. So we can easily compute the global displacements U1, U2, U3 as the product of the inverse of this 3 by 3 matrix and this global forces matrix. So solving for the global displacements, we have the inverse of this 3 by 3 matrix here times this global force matrix, which is a Coulomb matrix. And the result would be U1, U2, U3 equals 2.010506 times 10 to the negative 5 meter. This is the horizontal movement, so that's positive, so rightward. But the unit is meter because we express everything in kilonewton and in meter. So meter. Then U2 is also in meter, the downward displacement, negative 7.128827 times 10 to the negative 5. That's not 110. Times 10 to the negative 5. Then the rotation is negative, so it means clockwise. So clockwise rotation. Naturally, it's clockwise because of this load here. So the tangent would be rotating clockwise because this is negative. Negative 9.114294 times 10 to the negative 4 radians. So that's it for the global displacements. Next would be the member forces. Member forces. A. Remember that the cosine is 0 and the sine is negative 1 for member A. BA. This is the guide for member forces. This is the formula. So you have to also evaluate these values here, although U4, U5, U6 are all zeros, but we must have the values here. So that's why it's tedious if you solve the problem in matrix. But if we have Excel or where we can easily multiply, because this is just matrix multiplication, and we have to define the value of each cell, then it will automatically give us the answers. So these are the values of this matrix here, 6 by 6 per member. Then we multiply it by the displacements. These are the displacements. Then we obtain the member forces. So for member AB, this would be the result. FP1 is the axial force of member 1. P2 is the shear and P3 is the moment. Remember, axial, shear, moment. So P4 is also axial on the other end, P5 is shear on the other end, and P6 is the moment at A because our one is B. So axial at B, shear at B, moment at B, or moment BA, then axial at 4, which is vertical, shear at A, which is horizontal, reaction at A, and moment AB. These are the results after we multiply negative 1 million times negative 7.128827 times 10 to the negative 5. That's the only value. You get 71.88. This is negative 1 million times U2, negative 7.128827 times 10 to the negative 5. The rest will be 0. For P2, it is 50,000 over 9 times this one, 2.010506 times 10 to the negative 5, then 0, then plus 50,000 over 3 times negative 9.114293 times 10 to the negative 4. You will get negative 15.079, and the rest is 0 because all these are zeros. So these are the values. Then for member BC, member forces of BC, the cosine is 1, the sine is 0. So let's evaluate these values here. Then these are the values for member BC. So for axial of BC, the axial of BC is the shear of AB. So we expect that the axial of BC is the shear of BA rather. So P1 is axial force of BC, P2 is shear force of BC. Then likewise, the shear of BC is the axial force of AB or BA. So that's why we have here 15.079. Again, the interpretation, the axial force of member BC is the shear force. The axial force of member BC is the shear force of member BA, although they only differ in signs. So that's why that's it. Then you have to add the fixed end forces. Remember, there are fixed end forces only for member BC. So these are the fixed end forces for member BC. So the final result would be this one, 15.079. The axial force of member BC is the shear force of member BA. And we have 71.288. The shear of BC is the axial force of member BA. That's why they are equal, 21.28. And so on and so forth. And the moments. So these are the answers for member forces. But the solution is very long because of this stiffness. It will become short, though long, if you define each cell in Excel. You make a matrix calculator. So that's all for the first example.
Okay, let's have example 6.2. Determine the nodal displacements and member forces of the frame shown. E is 200 gigapascals, moment of inertia 500 times 10 to the 6 millimeter to the fourth, and area 30,000 square mm. So here is the given figure. There are 3 degrees of freedom at B. We call this node 2. And we mark the nodes as 1, 2, 3, 4. So there are only 3 degrees of freedom, so this can be managed by your calculator. So first, let's have the fixed end moments, fixed end forces. the positive direction as shown. So call this force AR, or shear just to the right of A, shear just to the left of B, shear just to the right of B, shear just to the left of C. So fixed end moment AB is fixed end moment BA by symmetry 30 times 6 square over 12, so 90 kilonewton meter. And fixed end moment BC is 44 4 square over L square, so 40 kilonewton meter. So fixed end FAR equals FBL by symmetry 30 times 6 over 2, so 90 kilonewtons, and FBR equals FCL is 40 over 220 kilonewtons because it is acting at the center. So therefore, for node 2, the moment is opposite to the net moment here. The nodal force is opposite to the net fixed end force here. So 40 minus 90 is negative 50. A negative is supposed to be clockwise, so it should be counterclockwise here. So that's the nodal force, which is always opposite to the fixed end force. So the vertical load is 90 plus 20, that's upward. So when you load it, it is opposite, so 110 downward. So this is the net load at node 2. So for the member stiffness, you're allowed to have this in your index card because it's very lengthy. Take note of symmetry also. So we input these values to each member. So this is the stiffness, global stiffness, global stiffness. Then for AB, you just substitute the properties of A here. Cosine of AB is 1 to 2, while its sine is 0. So this is for member AB, cosine is 1, sine is 0. For member BC, its cosine is 1 also, sine is 0. For member BD, its cosine is 0, but its sine is going down, so negative 1. So substitute here. So these are the values. If you input these properties into these values here, so these are the values. For BC, substitute cosine is 1, sine is 0, and the moment of inertia and area. Moment of inertia should be in meter to the fourth, and area should also be in meter square. You just convert. So divide area by 30,000 by 1,000 square to make it meter square. Moment of inertia, you divide that by 1,000 to the fourth, so that you will arrive with these values here. So that's for BC, stiffness of BC global. Then for BD on the next slide, so you just pause, then verify these values, and you look at the displacements also. So for BD, substitute its values. Cosine is 0, sine is negative 1, and you will arrive with these values. Node 2 is 456. So for 456, you add 4, this is row 4, column 5, row 4, column 6, and you will arrive with these values. These are the global forces. Remember, 0 horizontally, 110 downward, so negative 110, and it was counterclockwise, 50 counterclockwise, so that's positive global force. Counterclockwise is positive. So from here, we can now compute the displacements U4, U5, U6 by multiplying the inverse of this reduced stiffness matrix with these global forces. So this is the inverse of the reduced stiffness matrix, which is 3 by 3. There are 3 degrees of freedom only, multiplied by the global forces, and that is equal to U4, U5, U6. So these are the displacements in meter, horizontally, vertically, then rotation in radians. So if positive, it is counterclockwise rotation. So the forces, this is the formula, and we substitute U1, U2, U3, 0, U4, U5, U6 for member AB. Then these are the displacements. Then we compute the forces plus the fixed end forces. Remember the fixed end forces for member AB. Then we get the member forces. So P1 is axial force on member AB, P2 is shear force, P3 is moment, then P4 is axial B to A, P5 shear B to A, then P6 moment B to A. And these are the results. Take note of these results because I'm going to compare this with the software results from RISA later. Then for member forces BC, cosine is 1, sine is 0. And we have U4, U5, U6, U7, U8, U9, which are all zeros. Then multiply plus fixed end forces. Then these are the forces for member BC. So negative 2.5711, and that's it. So this is 3 by 3, but if there are 6 more than 3 by 3, then you will find the matrix solution very lengthy and tedious, that it is not recommended for manual solution. It is only good for 3 by 3, but beyond that, you will only appreciate matrix if you have a matrix calculator or a software, because on the first place, it's very difficult to memorize the member stiffness matrix, plus you have to add and you have to solve simultaneous equations, invert it, especially if it is more than 3 by 3, so it is really boring. It's better to solve this using classical methods in structural theory. But you can only appreciate this if you have a software or you make your own matrix calculator, which is your final project. That's it. Then let's have here member BD, cosine 0, sine negative 1. And this is the guide for member forces. And these are the results. Then this is from RISA software. These are the results, and you compare the results from earlier for member AB, BC, and this is for member BD. For member BD, look at the results, it's the same. This is axial, then shear 5.999, then we have moment. The only difference is the sign, but they're the same. So that's it. Then these are the displacements you compare. So for ISA, this is only for 3 significant figures in mm. Our answers before was in meter, and you compare. Our results were accurate than this because this is only for 3 decimal places. Then this is part of my matrix calculator. I will not share my matrix calculator because you might copy it. You do your own matrix calculator because you now have an idea how to make it from beams. you just extend one additional or two additional size because this time the area is considered. And these are partial member forces because I haven't yet included the fixed forces here. These are the fixed forces. Then this is the final member force. So which is the result here plus the fixed forces. So this is the structural stiffness or the global stiffness matrix, general, including the global displacements, to give you an idea on making your own matrix calculator, which is your final project. So you just look at the results and compare it with the results earlier solved manually.
So this is problem 6.6 of your handouts. So definitely we have 3 degrees of freedom at D, another 3 degrees of freedom at D. So that makes it 6. So you may use your you may make your matrix calculator, or you you solve this manually by using Excel in inverting 6 by 6 matrix. You will be forced to invert 6 by 6 matrix because after that, for member forces, you can easily multiply 6 by 1 or 1 by 6 with 6 by 1 matrix, or row matrix with column matrix. So I'll solve this using my matrix calculator first, but there is one problem in your quiz where you have to solve, you have to invert 6 by 6 matrix because you don't have yet a matrix calculator. So I input for member 1, which is marked A to B. So member 1 is A to B. Remember, it is just a frame or door frame. So A to B has its cosine 0, remember? Then A to B, it's upward, so the sign is 1. The area is 0.03 meter square, 30,000 mm square. The length is 5. The moment of inertia is 0.0005 or 5 times 10 to the negative 4 meter to the fourth. Modulus of elasticity is 200 times 10 to the 9, or this is the value. Then when you input this in the matrix calculator, automatic this will be generated. The global stiffness, the global individual stiffness matrix for member 1. Member 2 is the horizontal member. So the horizontal member is, the cosine is 1, the sine is 0, and same E and I, everything is the same. So automatic this will be generated. For node 3 to 4, or this is member 3, C to D, the cosine is 0, the sine is negative 1. So member 3, the cosine is 0, the sine is negative 1, area, length, the same. So this will be automatically generated. Then there is only a load in member BC, so you can easily compute the reaction and the fixed moments rather, for that member. So I did not show it here, but you can easily compute the fixed moments because the only load is concentrated. So use negative PAB square over L square for the left, then PA square B over L square for the right. Remember, at the left it's counterclockwise. The effect of the load is counterclockwise, and at the right side it's clockwise. Then the nodal forces will be opposite to that. So there will be moment and downward load at node B. Then at C also moment and downward load. So This will be the fixed forces, remember. So moment left is for member 2, 10.24. Moment right is negative 2.56. Then the shear or axial forces or the fixed forces upward. So 14.336. Then here it's 1.664 because the load, which is I think 16, is close to B. So that's why we have greater force at B. If you add 14.336 and 1.664, that should be equal to 16. Then remember, these are fixed forces, and therefore the nodal forces would be opposite to these values here. Then this is the elemental stiffness. Then we have here the partial member forces, which is the elemental stiffness times the beta. So we multiply this matrix here, 6 by 6, with the beta matrix and the global displacement matrix. These are the results of the global stiffness matrix. It will give us this partial member forces. We do not yet incorporate the fixed forces here. But for member AB, there are no fixed forces. That's why expect that whatever would be the value in the member partial forces, that also the final member forces, because remember, member 1 AB has no fixed forces, so that's why it's the same. Except for member 2, there are fixed forces. So these are the displacements for member 2 and 3 because it is 4, 5, 6, 7, 8. B and C have global displacements. These are the results, global displacements here. And this will be automatically generated here after the overall stiffness matrix, where we can find the global stiffness matrix. And member 2 have fixed forces. For axial, it's none, so the axial value is the same. But for shear, there was. So negative 1.328 plus 14.336. If you can remember, it was 14.336. So that's why it's only 13.00798. Then for moment, negative 5.45763709 plus the moment, which is 10.24. So 10.24 plus negative 5.45768 will give us 4.7882362906, and so on and so forth. Then for member CD, there is no load in CD, so there are no fixed forces. So whatever is the result in the partial member forces, that's also the final member force of member 3, which is CD. So for the global stiffness matrix, this is the global stiffness matrix. It will automatically generate, and we only need, these are the member forces, by the way, the global nodal forces, nodal forces. Then we are only interested of nodes 4 to 9, 4, 5, 6, 7, 8, 9. So it's 6 by 6 here. Then the inverse of that multiplied by this global or nodal forces, it will give us these values. Then the 0, 0, zeros there are placed manually because this corresponds to zero displacements at 1, 2, 3, and 9, 10, 10, 11, 12. 10, 11, 12. 0. Zero displacements. This is example 6.9. Determine the member and moments and reactions for the frame shown. If the load is acting at a joint, then there's no need to compute for fixed forces. All members will have no fixed forces. Like this one. If it is acting here, if we make this node 1, node 2, then the only force at node 2 would be the axial load or horizontal load, which is 120. The rest will be 0. Although the reduced stiffness matrix is again 6 by 6 because At node 2, we have three unknown global displacements as well as at node 3. So that makes 6 by 6. So for the individual matrix, so 1, 2, 3, 4, 5, 6, there are also three members. So for 1, 2, 3, 4, 5, 6, remember the cosine is 0.6, 3 over 5, because the dimensions 3 horizontal, 4 vertical. So the length is 5. And the sine is 4 over 5, so 0.8 positive. The area, then the length is 5, moment of inertia, then the modulus of elasticity. Then this global stiffness matrix for member AD or member 1 will be automatically generated because this is a matrix calculator. This is the beta matrix for that element AD. Then these global displacements are solved after the global uh, or structural stiffness matrix together with the load, which is only 120, going to right at 4. So for member 2, the cosine is 1, the sine is 0 because it is horizontal. For member 3, the cosine is 0 and the sine is negative 1 because it is downward. Then these are the generated individual global stiffness matrix, the beta matrix. Then we have here the member forces. There's none for all members because the load is acting at a joint and it is horizontal. This is the final member forces, which is the whatever are the results in the partial member forces, because there are no fixed forces, so they are the same. They are the same. These values are equal to these values because there are no fixed end forces. Then the global stiffness matrix is this, and you look at the load, look at the shaded part, which is 6 by 6. That is important to be inverted, multiplied by this force matrix, and the only value is 120. The rest will be 0 because remember that the load is horizontal, acting at a joint, so it cannot produce moment, shear, or whatever. Then that's why the only global force is 120 positive rightward. So these values here is defined as the product of the inverse of this 6 by 6 matrix times this force matrix here. Then automatically it will generate these values. Then you put 0, 0 at 1, 2, 3 here. Automatic also it will give you these values here because whatever is the value here, this is AL. What is the numbering here? I think this is AL1, 2, 3, AL3. So you have to define this equal to AL3. So whatever is the value in AL3 here, that's the value there also. So this is AL4. So this cell is defined as equal to AL4. This is equal to AL5. This is equal to AL6. This is equal to AL7. This is equal to AL8. Then this is equal to AL6, AL7, AL8, AL9, AL10, AL11. This statements here. Sorry, AL12, AL6, AL. What's the numbering here? Assuming this is 1, 2, 3, 4, 5, 6, 7. So 6, 7, 8, 9, 10, 11. So tama. So AL6, AL7, AL8, AL9, AL10, AL11. This is AL9, AL10, AL11, and AL12, AL13, AL14. So that's automatic also. You have to define that also if you make a matrix calculator. So that's why if you have this matrix calculator, regardless of the solution is long, it will be short because all you have to do is fill in this values here, but it's very easy. What is difficult is the definition of this matrix. So in Excel, there is a command there where you can also copy that result to these results here, that result here. So that makes it easy. So that's all. This is our last meeting. I'll give you your last uh, quiz, quiz 6 about frames, but do not expect, or if this will come out in your exam, don't you worry, I'll allow you to have the index card, and there will be no problems where the degrees of freedom is more than 3 by 3, except for this, for your last quiz, because the deadline will be on Friday pa, 6 p.m. So you can evaluate the inverse of a 6 by 6 matrix. So do you have